Hello everyone, and thank you very much for the invite. I'm very happy to be here and talk about machine learning and data literacy in general, with the focus on application and engineering and design. Originally, I'm a systems engineering. Believe it or not, systems engineers are kind of nomadic. They have a kind of nomadic life, and I had the same setup. So originally, I studied systems engineering in the context of manufacturing systems and supply chains, and then my bachelor and master thesis was all around these topics of machine learning. My first book was Tom Mitchell's book of machine learning, and yeah, in 2006-07, I started working on reinforcement learning. But at the same time, I felt that because of the nature of machine learning, I was attracted to the industry. So I worked for almost 3 years in the industry as a consultant, and working on system design in the context of enterprise and organizations. And then that was my naive understanding of architecture that brought me to architecture, because I was working on the topic of enterprise architecture, and it's all about how to join things together in architecture of the enterprise. And then I got interested in architecture, so I came to Department of Architecture at ETH Zurich, and then I did my PhD at Architecture Department. So from 2011 until today, I'm working in these fields of applications of machine learning. We call it digital literacy overall for architects, designs, and urban applications. So my talk today will be, I would say, a bit compact and fast, because I want to show a kind of an overview. What are the possible applications that you can do with it? Before going to the application, I would like to quickly tell you my readings of what is machine learning for me. And I would like to separate two modes of thinking that in computational, two paradigms of computational modeling. One I would call when you focus on representation and model first, and then you go to the coding or numerical approximation. This is the more traditional approach. And the other one that I call questions and data first. This is the change in machine learning. So if you think about representational approach and model first approach, I think history-wise, you can go back to Lagrange, Euler, and then, for example, books like Analytical Mechanics, that they are trying to represent problems, or even go back, you can go to Descartes in Analytical Geometry, that he tries to really find atomic problems and to somehow go bottom up and build a kind of representation of all the possible problems. You see the same approach in Analytical Mechanics of Lagrange, where, for example, he divides problems to statics and dynamics and then go through them. And then in the computational world and the numerical approximation of these analytical approaches, we have different methods developed. For example, methods which are all usually based on systems of known equations or differential equations. For example, in the case of structural design that I will talk about today, you always deal with systems of equations. Or when you go to computational fluid dynamics, you need a set of systems to represent these differential equations. And the rest, computing is just, in a way, numerical approximation. And then over time, you have these kind of steps. For example, from centralized models, we go to rule-based systems like cellular automata, and then agent-based models, and so on. And then, for example, in the case of urban systems where you don't have this kind of representational model, we usually end up building up this kind of layered, rationalized, and also idealized representations. And then the rest is a simulation. So if you think about modeling like that, so this is the first paradigm. Computing is automation or mapping of knowledge. So as you see here, you need to wire up the things. So this is your expertise. You know the system. You can represent it. And then you have numerical methods to simulate, for example, the game. Of course, you can put it in the context of optimization, and then you have concepts like simulation-based optimizations or constraint-based optimization or system identification, parameter identification. And then there's also a lot of dispute here that you can see that a lot of topics in machine learning are coming from this field. But the key point for me is that here the focus is on knowing. So you need to know the system first, you need to build it, and then you go further and simulate. There's a turn, and I think this is important. Sorry, I made a mistake. Okay, there's a turn that you'd say, what if we just focus on the questions and be completely opportunistic? Don't automate system, but let's see if you can learn the system. This is very, very ambitious. And then I think the first works, I would say, you could go back to 1804, methods like least square is coming here, because it's not anymore representational, but you just want to minimize this least square error. And this is a big change. And later on, I would say there are some papers, seemingly unpublished works of Alan Turing, also named unorganized machines, which is somehow ambitious like this, that what if instead of working like this direction, we go backward, we say what we are interested in. This could be any questions, any sort of error that you want to minimize. And then you are open to any source of the data. You're open to any possibility of the rules, because here you have limits in representation in complex systems. But here, in principle, you can learn kind of probabilistic setup. That's the idea. But it didn't work for many years. And then we know that machine learning is data demanding, also computing demanding, and it took us until today that now everybody is talking about data, but it worked in a way. So it's not just this basic idea. Of course, there are lots of contributions, and then always also there are lots of debates whether machine learning is just statistics or is just optimization. Nowadays, with automatic differentiation, people say, yeah, you can just automate put this in a kind of autograd loops, and then it works. But then you have people from signal processing or linear algebra, they are bringing these kind of priors, like when you have convolutions, you simplify the optimization problem a lot, right? So there are lots of works, which I'm not going into it, but I'm just saying that this was a lot of work from 2000, let's say 1950s until today, and we are here. And then if you just summarize it quickly, you have this kind of developments, 3 stages, I would say. You have linear and centralized models, like a classical regressions. Then we have local linear and decentralized models. And then nowadays, we have deep and distributed models. And then there's always this debate about model explainability and the model capacity. So my question is not from the point of view of a computer scientist who is developing new algorithms, but from the point of view of applications. And if you start as a student of architecture or structural engineering or any other fields which are not, I would call them non-computer science, you see that machine learning itself is evolving like a swarm. And it seems like there is a kind of gradient descent within the society, that when some topics is becoming viral, people work on that. And then if you want to start, it's really difficult. For example, we have methods which is amazingly powerful and conceptually beautiful, called GAN, and I think next talk, I hope Ali will talk about this. And it's a very beautiful concept, but imagine if you start as a non-computer scientist, and then you just see different types of GANs, and then you become a kind of opportunistic person, market-oriented person, because then you say, nowadays is GAN. I believe there is a reason for that, but if you are non-computer science with no background in machine learning, you might start immediately here, and then it might be very, very confusing. So the theme that I want to talk about is literacy. And literacy means that don't think about machine learning as an expertise, but think about it as a way of reading and writing the word. And then if everybody is able to read and write the word with data and machine learning, then masterpieces will come next level. It doesn't mean that by reading and writing you are a good author, but mastership will come the next level. So from here, I will show you quickly a typology of applications in the context of design and architecture, and then I will try to show limits and benefits of this machine learning. So a lot of applications, we have representational models which are valid, but they're slow. For example, this is also is not a really new topic. It's called surrogate modeling, for example. That we have these simulations, for example, for wind flow simulations or air flow, for example, water flow or similar flows, but they are slow. So here I believe there is a lot of things you can do with machine learning, especially the new ones. For example, one application is the physics-based simulations in urban flood and, for example, wind. And the context I'm interested in is, imagine you're an architect, you're responsible for part of a master planning project, and you want something fast, quick, and to tell you some hints. If you have this kind of generative models for this area of the city, what are the risks of flood? What we have from the physics-based engine, it's very minimal, in fact, and it's beautiful because it's just few equations, and then you just need a digital elevation model or a digital surface model. For example, in this case, for a certain region in Zurich, we need rain patterns, and we want to know the sensitivity of flood depending on this rain pattern. So that's the ideal setup. But the moment you increase the resolution, these models get extremely slow. And then imagine in a case that you want to have an interactive setup, that you might change everything in a matter of in an interactive way. Any of these simulations for an average size catchment area might take few hours. That you say, okay, what if it rains like that? And I want to just know what is the maximum water flow. And here you see that even though the model is good enough, but I mean it's valid, but it's not working in reality. So what we do here is that, in principle, the idea is very simple. We try to learn the relationship between this DEM or DSM, rain patterns, and maximum water depth. Here again, in order to make it faster, we can't claim that we are predicting directly the whole flow of rain or water on the surface, but we just say what is interesting for us is the maximum water depth. No matter when this happens, what if we are able to predict this thing? So here what we do is, in terms of AI, in terms of machine learning, it's quite straightforward. We have a region. For example, this is an area in Zurich. It's Lucerne in Switzerland. And then we cut them to patches of small patches, spatial patches, and then we have rainfall patterns. So we take few simulations, and in this case, also part of it, we have data from real rain patterns over time, and then we measure what was the maximum water flow, and then we train a model here, segnets joined with the rainfall pattern. So you have segnets encoding, decoding, and then you have this rainfall pattern. And the idea is that I want to have an interactive model that when I change the rainfall pattern, immediately tells me what are the risky areas. And of course, it's not risk, but it's just maximum water level. So in a more detailed way, that's the architecture of the model. You have small patches, spatial patches, here in this 256 by 256 by several analytical layers like curvatures and so on. And then we somehow reshape the rain patterns in 1 hour of rain intensity. And then we say, if this is the input, that was the output, and this was the rain pattern. So we feed it with several cases, but it's not a prediction of the dynamics of water. It's just predicting the maximum water, to be clear. So I don't have a real time now, but because of the time, interactive presentation now for you. But now we have almost nearly real time from the simulation that would took 3 hours. Each rain pattern, for example, if you have this rain pattern for this catchment area in Zurich, it takes almost 3 hours with the fastest computer we have to tell you what happens in terms of maximum water flow. But now we have it almost 2-3 seconds with delay. So the moment we change the rain pattern, it will change the flood level. So the limits here is that we compress the time-dependent dynamics, and that's a big problem. For example, we wanted to test this model with several catchment areas and then try to come up with a kind of universal emulator, but it's not working. So at the moment, it's just limited for a certain catchment area with few rain patterns, historical data, and it works pretty well. It learns to interpolate in between. But what we are now doing, and it still is ongoing experiment, is that we are predicting using something like convolutional LSTM. We are trying to predict the time dimension also. The second type of applications, which are, again, a kind of generic applications, are when you have fast theory models with nonlinear behavior. So, for example, this happens a lot in the context of structural design. You don't have a problem of speed anymore. You can generate things that you like, but the problem is that the behavior between your input parameters and outputs are always nonlinear, even though they're analytically defined. So in the context of structural analysis, I don't know how many of you are familiar with this field. The classical approach is that, and it's always a debate and fight between architects and structural engineers, who comes first. So architects want to come up with a fancy idea of form, and then they send it over to structural analyst or engineer, and the analyst will go through, for example, FEA or something like that, and they will tell you, okay, this is not going to work, but you need to modify it like that. This is the classical approach, but now there are other methods starting from, I would say, around early 2000s. We have methods that now change the game. The assumption is that you are a computational designer, and then you start directly with the force and topology. And then you learn, if you change the force distribution in the certain topology, which kind of form will come out. The promise of this method is to give you interactive models that called structurally informed form generation. So it means that whatever forms that you design, they are structurally valid. But of course, they're in a very, very early stage of the design step. So one of these methods, for example, is called trust network analysis. And the idea here is that this is a topology of the structure, and this is the force density flow in that structure. As long as they are in equilibrium, considering the external forces and the boundary conditions, you know that you can build this system. But the problem is that you don't know, if you change a bit of this force flow, you don't know what happens to the form, for example. Sometimes the volume might be super huge, sometimes some areas might be bumpy, and so on and so on. And if you think about it mathematically, you have a system of equations which is indeterminate, which means that the number of variables are more than the number of your equations. You need to force them somehow to add extra inequality or equality. And then after that, you solve the system of equations, but you don't know what is the effect of any of these input parameters to the final form. So even though it looks interactive, but it's not understandable. So that's what I call nonlinear behavior. Or similar methods that I'm working with my colleagues at UPenn is in the context of 3D graphic statics. Graphic statics is a method developed by Maxwell and Coleman in 1864. And the idea is that you can make interactive connection between force diagram and the form, so that you can play with them. If you change the force distribution in a structure, it will tell you what happened in the form, and vice versa. But that's the idea in a simple cases. But the moment you increase the number of connectivities, again you have this kind of sometimes like the butterfly effect, that they are really interdependent. And the moment you change any of them, everything else will collapse. So in this case, you have then I'm trying to be abstract, otherwise I could go to the details. Here we have 3D graphic statics, and then we have a polyhedron which represent the force. And then as long as they are in the equilibrium, you can build the form. But again, the problem is that you are changing the topology here. The previous case, topology is fixed. In this case, we are changing the topology by subdividing the forces. So for example, if the force is really high, we subdivide it to smaller elements, but by that, the topology is changing, and you don't know what happens to the form. So these are the main challenges. In the context of trust network analysis, we have statically indeterminate systems, which are very sensitive to the chosen force densities. So you have a fast method, but you don't know how it works. That's the problem. If you go to 3D graphic statics as an example, you have combinatorial explosion in the subdivisions. So you don't know, for example, how many steps of hierarchical steps you need to subdivide in any of these, for example, phases, where you should stop, and so on, and what are the final effects on the form. So the typical idea in terms of machine learning is to control this process via certain structural performance measures. And this is called performance-based design. And it's not an optimization, because you can also put this framework into optimization and try to minimize, for example, the weights and buckling and many other structural measures. But the idea here is that what if we just build a certain surrogate around the area of interest? For example, we know that we want to minimize the load path, which is the overall volume of the structure. So can we learn this? And then in the end, we have a very tiny interactive model, which tells you that if you change in this area forces, it's not going to help. You should not do it. If you change it a bit like this, yes, it's going to help. Because the idea is that it's not about optimization. You want to play with the forms in the context of architectural design. So we build surrogate models, and depending on the way you build your surrogate models, there are different ways to handle this problem. So for example, this is a recent work we are doing with one PhD student, again at UPenn, that we are coming up with an iterative sampling procedure that we start with random samples, but then after sampling, for example, we train a neural network that learns these subdivision rules, relations to two objective functions. One, what we call constructability, and the other one is a structural performance. And then when you have this surrogate, even though it's not accurate, we are very fast. So in a millisecond, we can calculate all the possible combination of the rules based on a certain limits that we define. And after that, we are interested only in the extreme values, minimum and maximum. For example, if you have two objectives, you're interested in the corners. And then we test those results in the corners, and then you go back. So that's a kind of active sampling in a way. And you could also do it random sampling. For example, the previous case on trust network analysis with the simple random sampling, you see that even though visually is not easy to understand its interactions, but the model quickly learns up to 98% for a certain topology what is the effect of any of these force values to the final form. And I think what would be proper in this case, which are not really developed, would be to go further to graph-based neural networks, and also in the context of reinforcement learning. Because when you have this initial topology, you can think about it that you have certain grammar and certain rules, and you can start subdividing them. And it's a never-ending game. So, but you don't know where to stop, and in which of these, for example, phases in this diagram, which is an arbitrary diagram, where to stop, and then depending on the final outcome. Another problem is that the final objectives are also case dependent. So a user might say, I care about this objective function. Another user might like another objective function in another context. So we can go further in this direction. But before going further, I would like to go back to this question, that does performance-based design captures creativity in design? Because if you ask architects, I don't know if there are architects here, but many of them would not agree necessarily, because usually you have masterpieces which are outliers. And then here you're systematizing them. The moment you make a system, you don't know if out of this system you can come up with a masterpiece. So that's a big question. And then I would like to refer to this sentence by Ove Arup, who says, a structural art is solving problems which cannot be formulated before they have been solved. The search goes on until a solution is found, which is deemed to be satisfactory. There are always many possible solutions, and the search is for the best, but there is no best, just more or less good. And this is a fundamental question that we can ask about machine learning, because it's really in contrast with a lot of assumptions in machine learning applications, that we have assumptions about objectivity. We know what is good fit, for example, and we have a measure of comparability, which is global, based on a certain representation. And think about it in the context of structural design, for example. How case person dependent is to compare two different structures or two different buildings. And this is not a simple problem, because it attacks one of the foundational assumptions of machine learning. As I showed you in the beginning, you start with a question, you want to satisfy that question through this gradient descent, but the question is that, as Arup says, after a while you change your objective functions. So how you want to build this? And if you take the whole system, give it to another person, they might do it completely differently. So even if you use the data is for the past, and then if you have a master architect, he might come up, or she might come up with another representation of the problem. So this leads us to another types of applications that we are developing, and it's about human-centered design process, where we put humans in the loop. And then the whole process is dependent on the human. And then human is the elements which is deciding all of these objectives. So for example, this is a case we are working with few students, and again, I'm collaborating with two of my colleagues at the chair of structural engineering, structural design at ETH Zurich, where we have been testing this case of designing a stadium roof with few students. And the idea is to come up with a methodology and at the same time to be able to come up with some creative results. So here, instead of going to these optimization loops, what we do is that we have a very fast parametric form generator, which is again based on this method of graphic statics. And in the beginning, we instead of generating few, we generate thousands of forms. For example, we start with 500,000 forms, and then we filter them based on quantitative measures, which is user dependent. And based on that, we start clustering this space. And it's very interesting because if you just look at the objective functions, for example, if you wanted to optimize this case of roof, stadium roof, based on a typical optimization function, which is load path, it ends up to very, very, in a way, boring forms, because that's how it works with this load path optimization. But when you say, let's look at these objective functions as a kind of soft constraint, but not in a way to minimize them, but to just filter some of the results that we are not interested. And the rest, we give this space. For example, this is based on a method I think you might know, self-organizing maps, which creates a clusters of forms, which are organized based on all of these factors. For example, here we use different measures of the structure. And then the user comes and selects a certain clusters. And then based on that, now we create kind of classification problem. We just say this area is good, the rest is bad. So then, because we don't have a global model between input and output, but now we can learn a classifier, which is a binary classification, and in a probabilistic way, it generates similar forms. So it's a kind of reinforcing loop, or it depends on the mentality of the person, could be also very diverging, because if you don't like what you liked previous time, this can go forever. But here, we put human in the loop, and we are building this system now, and then we are testing it with different students, and hope soon we can release the codes available for public. The third types of applications, which are close to urban applications, are when we have multifaceted problems, where we have no representational model at all. And these are, I would say, majority of data-driven applications, which are out of the scope of one single simulator, and they are between several domains. So for example, think about urban dynamics, think about urban air pollutions, think about urban economy, or for example, real estate, or think about urban energy and consumption. And even think about like air pollution, why air pollution happens on a street level, and it's very volatile. And then can we merge, for example, Navier-Stokes equation of large AD simulations to cultural habits of people if they cook at home or not? This is the limits that you clearly see that they don't work together. And this is at the same time the area that you see going back to this concept of model first, data first. Nowadays, we have this amazing ecosystem of data providers. Some of them are commercial, some of them are not. Some of them are open source. For example, OpenStreetMap that I love. It's for free. It's a whole planet. I will show you a few examples quickly now. But again, the mindset of thinking about representation or thinking about questions will change the game. So on sorry. Too much design. Sorry. If you think about digital twin in cities, you start from here. You start first assuming what is a city. I want to represent the city, so city has this, and this. And you build up complicated software applications. And this is the traditional approach in urban design, which is still happening. And now with big data, you assume that, of course, I can make a digital copy of city, for example. But then if you think about the other way, and if you say, I don't know what are the representation of the city, what is the image of a city from anybody else's point of view. So if you think about it like that, we don't need anymore to build a model anymore for the cities. And this is what I call question-oriented or data-driven approach. And this is the way, for example, you can think that internet is working. Because in the beginning of internet also, we had this approach of thinking for semantic models of internet. And now the other way would be to say, no, if you have a kind of protocols that they can talk together. And then Google came up with the idea of, for example, PageRank, that is not based on the semantic and content, it's about the structure. It was a breakthrough. And now the same thing is happening in urban design, that people are starting building semantic models of cities, whereas cities are complex, and because of that, they're beautiful. If the moment you put them in a model, they are not anymore interesting. So, for example, I show you a few examples. One is what I did in 2016 is to test what are the urban forms in the world. For example, classically, architects are familiar with this model of Cedric Price to compare city forms or urban forms with the way you cook egg. For example, you have boiled egg for ancient cities that you have a center, you have urbs, and then you have hinterland or farmlands around the city. Then you have industrial cities, which are around armatures of the cities, like highways and connectivity. And he calls it sunny side up or fried eggs. And then you have scrambled egg cities, which are ecological cities. Though you have urban farming and the roof of your house, so it's everything mixed. So that's a very, very abstract and interesting typology of urban forms. But again, it starts with this mindset of having a model first, and then you teach students first based on models. But it depends on the context. But I'm just make a kind of a connection. So what we did, and it was very simple to do, is we took this opportunity and then we took data from OpenStreetMap, data from urban forms of more than, this is in end of 2016. That time we had 1.1 million locations of cities, towns, and villages. And what you can do is that you literally test this. It's a very simple game, but we took images of road networks of these 1 million cities. And of course, you cannot sort them manually. You can feed these to a kind of autoencoder model. And this autoencoder model is able to find similar forms and then gives you a dense vector. If you cluster them, it gives you something like this, which is a kind of topological data analysis. It tells you that these are small villages. The majority of world lives here. And these are unicorns. For example, a lot of them are Japanese cities, which have very different urban forms. So compare this with the city as egg model. So this is pure data-driven. It's observer-dependent, and it can be case-dependent. Depending on your question, you might be interested in different types of form, right? So then here again, talking about generative approach or indexing approach, a friend of mine, when I did this, told me, can you just think about it like a master plan generator? Because now I have an autoencoder, which I feed the image itself, it predicts itself. But what if you just say, I have the area around the master plan, and then you predict the middle? So if you can do it with a lot of cities, you should be able to generate, you build a model which generates what it would be in between. So if you have an empty plot of land in one city somewhere in the world, the model should be able to generate. So then a key question is that should we do it or not? One way to think about it, technically, yes, it's possible. But if you think about it, that cities are concrete and complex cultural product, the answer would be no, we should not do that. And then that's the idea of indexing the world. And again, because this tendency between model-based approach and data question-oriented approach is always there. And then I see a lot of applications which are trying to take this approach, go to the generative part, whereas the other approach would think about indexing, create a search engine for cities. And now if you have the whole big data set of the whole planet, depending on your question, you can build different types of search engine and in a moment, and then you just throw it away. For example, what I did recently is that for commercial real estate sites, we want to know if you have a plot of land and you're in a very, very early stage of design, can you find a similar place in the world? Because they might have some ideas there. And you can use this type of OpenStreetMap data set, and also you can add other Street View imagery. And then you can build a temporary search engine. So the search engine, it depends on your use case. So you can build and go on top of that. So for example, here you see that if you take any of these cities, for example, it will find unique cities in the world. None of them are generated. They are real cities in the world. And interesting is that nobody knows all of them. So you can continue like that. For example, you can build this kind of methods. For example, I'm using OpenStreetMap data. This is last year. I don't know the recent data. We had 320 million buildings, data from OpenStreetMap. They are not complete in any way, but you need to really play with them. You have different types of resources, point of interest, and so on. And you can build these layers for the whole planet. For example, if I have internet, which I have, luckily. So for example, this is the map of the... So this is London, for example. These are all the buildings which I had last year. And then on top of that, you can add, for example, any questions that you have. These are now really cheap to do it if you know how to do it. And the thing is that it's not just for London, it's for everywhere. You can say access to transportation, access to, I don't know, place of worship, access to any types of question you can come up. I will show you in a second that you can generate 200 different types of analytics. So even act of analytics is temporary because you say, I have the whole planet. I don't need a model anymore. I'm not afraid of not having a model. So you can really be active. So for example, this is the model I just tested before coming here. So this is data from San Francisco. So these are, again, for simple visualization, few layers, but you can add many of them. So what I did is that now I have access to this data recently published by Google. They use their Street View machine images, Street View cars to also collect air pollution. So now the question is that, can we use the previous analytics only for this application? Because we don't know if there is any representational model describing relationship between urban factors and, for example, air pollution. In this case, this is the map of San Francisco for PN5, for example. So again, what we did, believe it or not, the code is the same code as for the case of water flow prediction. In this case, the input is 38 layers of patches of cities. And then we calculate all of these analytics which are relevant. For example, car speed, access, height of the buildings, density of the building, distance to transportation, distance to restaurant, and so on. This is this kind of domain knowledge that you have. You build them. And then you feed it to a SegNet model, in this case. And these are not validated results because I just finished it last week. But you see that here you have the prediction, and here you have the true values. And the model works very well. So I'm a bit suspicious because of that. It's too good. But the thing is that now we can use this model. So we have overlapping patches of the city. Then we can create a kind of probabilistic map of air pollution. And on top of that, since the SegNet model is very fast, I can start playing sensitivity analysis. For example, I can calculate the average distance of every house to the transportation, and you see the effect, which is considering all the other factors. So these are the models that I call data-driven simulations or data-driven analytics, which are very, very case-dependent, and you cannot advise this as the way people would say how Navier-Stokes model works for water flow. This is the case for maybe San Francisco only, but if you have data for the whole planet, you can build it. And the same question, you can think about real estate price, any other factors in the city. So I just want to go to conclusions. And I tried to show you a wide range of machine learning applications. I tried to show where they are beneficial and where they are the limits. So there are a small part of the problems in terms of complexity. I just call this cone of complexity. When the goals or stakeholders are increasing and at the same time, which are dependent, number of variables and relations are increasing, problems become complex. And this is the majority of the word problem, right? So the amount of representational approaches we have from classical science is here. And then I try to show you, for example, if in the case of computational fluid dynamics, it works. If it's fast enough, you don't need machine learning. But if you want to speed up, you can use it. If you go further, there are cases that you need to have data and theory both together. And then majority of the word problems related again to urban problems are here when you really don't know any representation. And it's all based on stories. And people know that. So I try to show you a range of possible applications, any of them, and how you can use them. And going back to this idea of machine intelligence or AI in design and creativity, I would like to create a kind of a dichotomy here that I would like to compare what is machine intelligence and what is human intelligence, for example. So machine intelligence, in my opinion, is finding answers, whereas human intelligence is finding questions. And I don't know if you can use machine learning, for example, to find a question. In that regard, machine intelligence is very well suited for areas that we have systems, rules, even nonlinear, or standards. And then opposite to that, we have human intelligence, which are working on art. And here, art, for me, is when you are resisting to be part of a system. That's the art. So by its definition, it can't be done by machine intelligence. So in that regard, machine intelligence will take over many of the jobs, will go to automation, definitely, but I don't think it will cover creativity, because creativity means, again, think out of the box. When you're out of the box, it should not be in the data. So it can't be, that's a kind of a self-referential setup. In that regard, I think because we are in an academic environment, I believe majority of the fields, the way we are teaching students or educational systems are around expertise, because it has been like that historically. We have told them how to learn answers for a certain domain. But if machine learning is going to find the answers, we should focus on something else. And then in that regard, I would say we need to think about what we can call mastership. And with mastership, with expertise, you never can be a master. And this is unfortunately the problem you see in a lot of engineering fields, whereas I found very, very fascinating in architecture is that they are trying to be masterful. And then by mastership, I mean you need to be mastership and, of course, digitally literate. Because then you learn how to play with all of this new development in machine learning. You need to be able to read and write any new algorithms, but it doesn't mean that you are part of the game. You can create a game. And so creativity happens there with interaction between human intelligence and machine intelligence. Thank you.
So do anybody have a question for Vahid? Yes.
Can you tell us how... Thank you for the talk. I was wondering, how do you think that these advancements are going to play, either data-driven or question-driven, into stylistic approaches in architecture?
Pardon?
Into style, how you approach the looks of a building or house.
Maybe I would say next talk would be more suited for this,
Okay.
because that's the connection of a human. And I think if you don't have humans in the loop, so you can define styles within your data, even hidden, but it's part of that. So then machine learning, in my opinion, can learn to automate those styles or interpolate in between. But if you believe, I mean, there is also discussion. I'm not an expert in art, but there are people who believe that, yeah, also artists are interpolating in between, even human artists. But there are also, based on my definition, which actually goes to, a definition comes from Gilles Deleuze, a French philosopher. This is the definition of the art, which is to resist, to be part of the system. In that sense, you need human in the loop. So that would be definitely the case as far as, I mean, based on the current technologies.
Okay, thanks.
Thank you for the talk. In terms of kind of machine intelligence and human intelligence and model-driven and data-driven, is another difference also, I guess, causation being able to be derived through human intelligence and not through data-driven intelligence?
I'm not sure it's the same. I would say, because I know a few methods that are trying to model causality compared to correlations. And historically, yes, because this is the way humans are doing based on causations. But I think this is an open question, and I don't know if there's an answer for that to say that I wouldn't agree that causation is on the human intelligence side necessarily, because a lot of time we also might do correlation-based decisions. I don't think there's this kind of division. The way I'm talking about human intelligence is not necessarily about causation or correlation. It's about that's about act of decision making, which happens on the right and on this side, machine intelligence side. It could be causation based or correlation based. But what I'm trying to talk about human intelligence is when you define the overall game, why you are trying to solve this problem. And then causation might be the next step, I would say. That's my reading.
Thank you.
Maybe next talk.
Thank you. I guess this is, and maybe it's helpful for me to say that I come from a sociology background, so put a bucket of salt alongside that. But I think what I've been trying to understand with these attempts to involve humanity in the algorithm, if you like, is, I guess, two strands. One is, here is, say, a design, and then people's responses to the design. And I guess there's an algorithm for generating a range of designs, but that has to, and I guess you can have a feedback loop there, right, of human preferences go back into that algorithm that then lead to other designs that might be derivative of the designs that get higher ratings. But yeah, I guess the extent to which it's always an algorithm that's feeding something to people. And maybe that's part of the next presentation, is if someone creates something and then an algorithm tries to understand it. So it's sort of like starting the loop in a different place from the people rather than from what the computer can generate. Though, obviously, from a data structure, it's much easier if the computer generates it itself. And the second thing is a sense of taste. So you can have, say, local maxima within some canvas or array of design features. And as you were already referring to, this person, this group of people perhaps may have a preference of taste at this point in time. And I guess that's where I'm going, is the extent to which preferences and aesthetics change over time.
That's right.
Whether boredom is even a word that's applicable in this sense. Oh, I've seen many buildings like that. Ooh, that's new, and that emotional response. So I guess that's a long way of asking how much you've thought about those ways of looking at the human intelligence in this context.
I would say the first part, I call that human as a user of the system. So that's different. What we talk about digital literacy is that, in principle, that user is able to build its own local temporal search engine, or let's call it assistant. You need to build your own assistant. Because data gathering, again, guessing, will be cheap if it's free. You can have your own crawler. You can collect the data overnight. Nobody knows what you're crawling. And then you build your own search engine. That's a mastership approach of using digital literacy. So first question is the user, of course, and it's by us, and then you have this kind of collaborative filtering and so on. That's clear. The second part is exactly the point, because there is no solution. And that's the point I want to raise, that when you go, for example, I have good designer friends. I'm not a designer. When you talk, you just realize that exactly the point of boredom is very, very important, right? And that's part of the game. And if you want to rationalize design, you go to design science, and then with all respect, good designers hate it, right? So how we can use these extended hands or assistant, personalized assistant in this process, this is an open question. There's a big questions, like, for example, in case of design studios, for example, that in the end students should come up with a design, there's a question that always you can ask, what if you didn't use data for this case? Yeah, it could be possible that you say, I used my own intelligence without using data. But it seems true that in a lot of applications, the ability of machines to sort out things for you, depending on the task you give, is better than human intelligence. So in that sense, it might work. Because I show you, in this case, for example, I show you in the case of structural design. This is, okay, it's not easy to go there. But it's like a 50,000 structural design, 50,000 scenarios which you can build. So sorting them out, or cluster them, is not a human job. So, which is happening nowadays. Now people click, and then they are the user of the system. The system gets better and better. But here the idea is that machine clicks for you, you decide, and then you move. And of course, as humans, we are not machines, and because of that, you might end up to very bad situations which are not close to what you decided to do. For example, you wanted to design a roof of a stadium, but yeah, it's possible that you don't do it. But that's the beauty of life, no? Otherwise, life is a machine. The homes and the stories about cities that I was trying to say is that if you build a copy of city, what is that city then? It's boring city. It's a machine. And then we have experienced this during the history of urban theories. When you have city as a machine, it's not necessarily a good city. Or if you think about the city as a corporate, again, it's not a good city. So yeah, definitely it should be open-ended questions, which makes the life better, I would say.
Thank you.
Thank you. It was very interesting.
Thank you.
For me, there's still one question that remains after your additional explanations, and that is, I see two sides of it. On one side, I see the technical aspect of the design, and on the other hand, I see the artistic part of the design.
Yep.
And I absolutely agree that the whole data-driven approach and so on can definitely inform and augment both sides of the coin. But in the end, the artistic notion of the design comes back to what you briefly just mentioned as changing tastes over time and so on and so on. But for me, it is interesting because what I see currently is mainly we're trying to replace both parts through machines.
Yep.
So even if Alan Turing Institute, sorry I have to say, but most solutions do not really consider the augmentation of the human abilities that we have inherent. We're more concerned with the research and the scientific examples that you show. How can I more or less understand air pollution in the city? How can I more or less build cities more efficient? And so on and so on and so on. But the parts of the city where I feel most home are all based on human making it something special. Humans making it something special, communities growing over time, and so on and so on. I'm just saying, I just find it interesting that you talk on that level, that it shows that there are two sides of the coin. Sure. But on the other hand, I feel we're always acknowledging that, but we're not really working towards it.
Yeah. Okay.
Is that correct? Or is
that's my opinion, yes. I think I tried to show that there are two sides. I tried to show the limits of machine learning. And I try not to use the term AI because I think it's a vague topic. And I try to, if I had another time to show the technical part of machine learning, would be to show that this is a continuation or another abstraction from after Lagrange. There is nothing more. And then, but the game changer was now you are focused on the questions. So I see this as a continuation of development in mathematics and of course computation afterward. But then there are applications that you cannot say that cities are just based on humans because that's a kind of very, very resistive approach that you see among like urban designers, for example. They don't want to know because they say, no, for sure it's not useful. But the question of, for example, air pollution, I don't think anybody knows exactly how this happens. So these approaches are helpful, right? And then the part that I try to briefly mention about indexing versus generative part is indexing means that you can learn from other cities. So if you are able to index air pollution of 1 million cities in the world and leave it to the society, like the way we have access to internet, so people can learn and people can find their own twin cities. This is a twin city, right? You find real cities, real communities, and you see their stories, and it's a very complex set. So in that sense, machine learning is helping. And without machine learning, you end up to city as egg, because you say, that's the abstraction I have, which is strong, but is limited. Because sometimes you want a very specific case, right? So now this indexing can help that. But definitely, if you stretch it further to say, OK, I'm going to replace architects by machine learning, I strongly disagree with that.
Well, it comes back to the old question, what is the purpose? Sorry, it comes back to the old question, what is the purpose of the machine? To be better as the human, or to help the human to be better at what he does? So I'm just finding it something that remains still an open question in a time where we actually make leaps and bounds in our technical progress. So,
yeah, I would say that's a very, very philosophical problem that has been discussed for many years, and I don't believe there is an answer, for example, for that. I mean, you can also refer to like problems like Hilbert problem, and then you have this Gödel's incompleteness theorem. It shows the paradoxical nature of it, but seems that that's a part of our struggle of life. It's beautiful, because the moment you're struggling, you generate energy. So if you think there is a final solution, there is a kind. I'm not a philosopher, but I know that there are, again, two camps of philosophy also. One group thinks that there is a foundation in the end, and the other groups say, no, the act of playing is the foundation. So that's an open question. And I think I try to create this kind of dichotomy to show that, yes, you need to be aware. And that's literacy. By literacy, of course, you respect machine learning because it's amazing. You can't deny that. But you need to know where to use it, how to use it, and so on. And the literacy, for example, maybe a bit too much, but think about it that if you think about a small village that nobody can read and write, you always have one person who is able to read and write. Whatever is the letters coming to the city, that person reads for them. So that's the literacy first. And that person might cheat. This could be the case that you are a user of a system, which is tyrannic, because they say the letter says this. When you become literate, then everybody can read and write. So you are in a different world. But then after that, you don't know where masterpiece is coming out, because everybody can read and write. But why some people write good books, why majority can't? That's it. I think open questions, and I don't know if there is an answer, but could be a question that some people could ask in terms of machine learning and try to build these approaches. Yeah.
Thank you. Very interesting. I would like to play a bit of a devil's advocate and ask, well, I think we're mixing up concepts about human agency and human abilities. If the machine can do it better than humans, then why not do
Exactly.
it? And augmentation has more to do with human agency and what is meaningful to humans, and that we preserve that as a priority, as opposed to not allowing machines to do something that they can ultimately do better. If machines create art or music that cannot be differentiated by humans, which is the human sort of artifact or creation, and the machine creation, then isn't it equally good? I mean, I'm not trying to say that human artists or architects will become obsolete. I'm just trying to say that if machines are able to create something that has an element of creativity, and even humans are not able to differentiate between the human creation and the machine creation, then shouldn't be trying to maybe take some meaningful pleasure and artistic value out of it?
Yeah, I agree with that. No, totally. But most of the time, you are ending up to doing interpolation between masterpieces. So the moment you do that, that's automation. But if you go beyond that, which I believe there are ideas to do that. For example, very, very naive idea that just came to my mind. A lot of reinforcement learning methods are based on these objective functions that you want to win the game. I believe there was once I saw this from OpenAI, that they developed this curiosity-driven. I hope you talk about this.
Yeah, which is evolutionary based, right?
Yes.
So best artist in the
Exactly.
universe is nature. So
Exactly.
yeah.
So if there's a brilliant idea like that, yeah, of course, I'm fine with that. But I'm just saying that think about the reason for showing that was to somehow try to scare engineers because the way this has been developed, also you can look at the works of Bertrand Russell and people like him, they try to create cells of disciplines, and then you are within these cells, so you don't need to know a big picture, but you are expert because you learn the rules of this part. So this is the way, for example, I was also educated in the first bachelor degree. And then when you go to architecture or art, you see that, oh, actually it's not like that always. You don't need to focus on certain area. And this is where I think if you think about these cells or frames as area of expertise, I try to say that with machine learning, I believe you can replace engineering a lot of time. But then if you go to the extreme, of course, it's the extreme case in art. I think if you define art as act of resisting the systemicity, then it's a paradoxical. You can't build it. And also, of course, you can expand. For example, one idea I mentioned was that we have always a global representation of objects. Whereas if you think about human agents, they might have their own representation of the world, and then they are communicating, right? So this can be a next step. I'm not expert in that field, but I'm just saying that this could be. But this is the beauty of this kind of dichotomy is that it creates discussion. So that was the main idea behind it. Do we have? Yeah.
Yeah. Well, thank you, Vahid, for
You're welcome.
your talk. So just to give it a little bit of, I wanted to mention this before, I completely forgot. So I first met Vahid in a conference he gave to a group of architects. And one of the big questions is, and one of the biggest struggles we have in architecture is how do you go through different design iterations in a fast manner to actually arrive at something. And you're always dealing with this time constraint. You want to explore as much design possibilities as you can, but with this temporal constraint. And one of the biggest benefits we saw in this type of approaches was exactly speeding up this iterative process of design, of where you're looking at one proposal, seeing how it might work, and iterating through many different other options. So thank you very much for that,
Thank
Vahid.
you.